Hello, and welcome to my talk on spacecraft line of sight, jitter management, and mitigations, lessons learned, and engineering best practices. My name is Neil Dene, and I'm the NASA Technical Fellow for Guidance, Navigation, and Control at Goddard Space Flight Center. Aaron Wolf is one of my co-authors. Aaron comes from the Jet Propulsion Laboratory. And lastly, Davin Swanson is our third co-author. He's the Technical Fellow at Raytheon Intelligence Space. To start with, I just wanted to briefly mention the organization that I belong to. It's the NASA Engineering and Safety Center. It was established in July of 2003 in response to the Columbia shuttle accident. It's built on three traditional safety philosophies: strong inline checks and balances, healthy tension within the organization, and value-added independent technical assessments. We primarily provide independent assessments of technical issues for NASA programs and projects. But the aspect of our organization that is relevant here today is that the NESC also performs discipline advancing engineering assessments. In this case, Jitter Workshop that we put together under my GNC team. So here are the objectives of the Jitter Workshop that we conducted in October of 2019. The primary objective was to identify and document and share lessons learned, best practices, and identify the preferred options for jitter-related activities in the following technical areas: spacecraft pointing system architecture trades and definition, requirements, definitions, and flowdown, modeling and simulation tools and techniques, subsystem and component characterization testing, spacecraft system level end-to-end testing, and overall jitter or microvibration risk reduction approaches and techniques. So we had a very broad agenda. A related workshop objective was to identify programmatic and contractual issues and barriers and challenges related to solving the spacecraft line of sight jitter problem. A fundamental motivation for the workshop was to address a common interest in developing an efficient process for consistently creating implementable, reliable, and well-performing solutions to the spacecraft line of sight jitter problem. Lastly, the workshop was an opportunity to share between NASA and ESA Space Agency viewpoints on jitter with the broader community and a chance to hear industry viewpoints on jitter. And the full set of workshop findings and recommendations is in the paper. This is our team that met, as I say, in October of 2019 for the NESC Jitter Workshop. These participants in the workshop included representatives from NASA, including JPL and ESA, along with industrial partners, independent consultant, subject matter experts, and members of academia. Looking in a discipline way at the participants, they included specialists in GNC, pointing systems, mechanisms, structures, finite element modeling, isolation systems, system engineering, and system testing. And many of these participants made presentations on a variety of relevant topics. So we had a good cross-section organizationally and a good cross-section from across the engineering disciplines that are involved in jitter. So let's see, this is an excellent chart that I borrowed from a 2011 JPL paper on instrument pointing. The reason I wanted to include this is to emphasize the point that the frequency of the pointing stability and jitter requirements are critical in determining the spacecraft design and to achieve these requirements. This figure is great, I think, because it depicts the jitter problem in the frequency domain in such an excellent way. At the bottom of the figure, we see a conceptual spectrum of disturbances that can affect the attitude of a spacecraft. Low frequency disturbances are generally external to the spacecraft, and they come from such well-known sources as solar radiation pressure, gravity gradient, and/or atmospheric drag. The high-frequency disturbances come from internal sources by and large, such as the reaction wheels and thrusters, or possibly a payload cryocooler pump. Each disturbance source can excite different structural modes in the spacecraft. Those structural modes are shown in the middle of the figure here. At the far left of the spectrum, we see the rigid body modes of the spacecraft, and on the right are the flexible body or elastic body dynamic modes. And these are typically due to solar array modes, or perhaps there are other flexible appendages on the spacecraft. The frequency of the pointing stability and jitter requirement determines to what extent these vibrational modes need to be stabilized, and which in turn determines the damping strategy that one would employ here to control jitter. At the top of the figure, we see a range of possible damping approaches. At low frequencies, of course, the spacecraft attitude control system, or ACS, is used to correct pointing errors. ACS attitude knowledge is typically provided with star trackers and inertial sensors, gyros. The actuation for attitude control is typically achieved using reaction wheels. Although I will say there have been some recent architectures that employ microthrusters for precision attitude control of observatories. In the cases where there's very stringent pointing stability requirements, jitter control requirements at the low frequency range, one might employ a more accurate way of getting attitude knowledge. In that case, we might use dedicated sensors on the payloads, payload instruments, I mean, and we can use those to point at a guide star and derive a reference, as I say, from that guide star. On that figure we're showing here, this approach is called payload assist. And the very attractive feature of payload assist is that it gives a direct knowledge of the telescope bore site error. And by providing a higher frequency attitude error feedback information, the payload assist essentially increases the effective bandwidth of the ACS, as indicated here in the figure. So as you can see in the frequency spectrum at the top of the figure, the capabilities of the ACS will not have sufficient bandwidth to correct attitude errors at higher frequencies. So vibrations in the higher frequency range are usually, as we know, are referred to as jitter. And high frequency damping of the jitter can be obtained either through active stabilization or passive vibration isolation. Most often, in my experience, I've seen it's passive techniques such as reaction wheel vibration isolators that are used to ensure that the disturbances from the wheel, in this case, do not affect the instrument pointing. So again, I just thought that was an excellent figure. Now, what we did was, after 2 days of workshop interaction, it kind of boiled down to 5 best practices that I wanted to share here. Best practice number 1 is to fully appreciate and understand the jitter performance challenge. So make informed architectural choices for the given pointing and pointing stability requirements. This should be done in collaboration with the mission stakeholders, i.e. the scientists, the principal investigators, and this is something that needs to be done early. Best practice 2 is to fully understand all the potential disturbance sources. Here we concluded that early tests, particularly for key components and subsystems that affect the jitter and the pointing stability, are critical as they allow for refinements to the system early in the design process. Consider all the potential versus expected sources of disturbances. Best practice 3 says to pursue an incremental jitter analysis and test program that mitigates risk over time. A successful spacecraft line of sight jitter management and mitigation solution requires an understanding of the behavior of key components through test. Understanding of the overall system comes through a combination of test and analysis consistent with the complexity, uncertainty that you face on your particular mission. So you have to apply some judgment there. Multiple ways to verify system pointing, stability, and jitter performance are needed. For complex systems with challenging requirements, I would say a comprehensive incremental testing program is required to anchor even the best analysis and the best models that you have. So moving along, the final 2 best practices we wanted to share here today. Number 4, build in flexibilities to overcome unexpected in-flight pointing stability performance issues. Ground test limitations, I think we all know this, push systems with stringent jitter and pointing stability requirements towards additional jitter mitigation approaches. And some of these can be redundant or potentially overly conservative to cover uncertainties. Alternatively, consider this. Operational flexibilities can be used to mitigate dynamic interactions within the spacecraft. However, these can be difficult to fully characterize prior to launch. Obviously, we're hard-pressed to do full testing in the 1G environment. Gaining insight into key system operational flexibilities and constraints requires diagnostic capabilities within the instruments or through additional instrumentation to improve pointing stability performance in flight, either by onboard adjustments. Best practice 5, include payload and spacecraft bus jitter measuring instrumentation to assess modeling and test results with in-flight pointing stability performance and to mitigate jitter with in-flight adjustments. Deploying in-flight the same precision instrumentation used during ground test could be critical for multiple mission programs. That's where there's a family of the same spacecraft. And for missions with stringent pointing requirements. This enables trending, operational updates, and anomaly resolution, and informing future designs, which is critically important. So here's a couple of other things we'll now go through that came out of the workshop. Jitter terminology, very interesting. The consensus view of the workshop participants was that there was no single commonly understood and used definition of jitter in the context of line of sight pointing and pointing stability. I guess that comes as no surprise to the audience. We feel there was a need to converge on a single set of definitions accepted and understood by the multidisciplinary community so that we can share and reuse the analysis methods. We could share the design methods and concepts, and it would just improve the overall system engineering process. The definition of jitter and related terms, they have advanced over the recent decades with multiple authors making fundamental advancements in the definition of jitter, and they are in the references in our paper. Lately, there's been a trend, it appeared to us, that jitter engineers are considering the use of the optical transfer function, or OTF, in the discussion of jitter definition and related terms. I would think any of you that have worked jitter problems probably have a solid understanding of this, that jitter is a systems problem. Managing jitter is a very multidisciplinary, systems-oriented task, and it requires the involvement of an experienced multidisciplinary team, particularly for the more demanding jitter requirements that some spacecraft have, namely at the nanoradian or picoradian level of jitter management. So this drives the need to create and maintain an experienced multidisciplinary team to manage jitter throughout the project lifestyle. This should include subject matter experts in both spacecraft and instrument design, as well as the science and ground system team members who are responsible for the post-processing of the instrument data. In other words, an end-to-end look at jitter problem. Jitter management and mitigation includes integrated modeling, simulation, and test planning, and that should be addressed early in the project lifestyle when you can make more impactful system architectural decisions. You got to get that done early rather than late, right? You can't just bolt on solutions late in the game. And we want to consider that excessive conservatism in the design and the requirements definition process should be avoided if possible. Margin should be addressed and held at the system level to avoid too many layers of margin across component providers. We always know there's typically examples of hidden margin. Okay, another key point that emerged was on the topic of onboard instrumentation and in-flight demonstrations. So this was a very lively topic and engaging topic at the workshop. GNC engineers have a need for in-flight jitter-related data. Being able to obtain and analyze in-flight system performance data would aid to validate pre-launch models and improve models for follow-on spacecraft. It also would aid in doing in-flight system adjustments. There was an engineer at NASA Goddard back in the 80s, very active individual in the jitter engineering world, really a pioneer. One of his mantras was engineers need data too. We all know scientists want data, and that's the point of all our missions, but engineers benefit from having data, and that was one of John's themes, and it emerged during the workshop, and we had a lot of discussion about it. So we felt, in partnership with industry partners and other space agencies, that NASA should initiate an investigative trade study into miniaturized jitter measurement instrumentation alternatives. Could there be a sensor package that could provide us the data we needed, gather the on-orbit data we needed at a lower price and risk point for individual missions, rather than having to do it in a customized way each time? So Another item that emerged was the Jitter Engineering Guidelines Handbook. There's generally no accepted engineering reference on managing and mitigating jitter. Some textbooks and references may touch on the subject, but the important process details of specific flight-proven methodologies and techniques, they're not readily available or accessible. So we felt as a group that there was a need to make the collected knowledge of these experts available to the next generation of engineers that will be faced with solving jitter problems on future space platforms. The workshop participants felt that NASA, potentially in partnership with industry partners and other space agencies, should initiate the development of a Jitter Engineering Guidelines Handbook, a handbook in which we could document the lessons learned and best practices for the analysis and testing needed for managing and mitigating spacecraft line-of-sight jitter. Modeling uncertainty factors. So I think we all know that modeling uncertainty factors, or MUFs, are used to add conservatism and to pre-launch predictions of jitter performance, typically before the flight system hardware is matured. The MUFs are used to capture uncertainties in the structural models, the disturbance forcing functions, and other areas where there's a potential dynamic interaction. Clearly, a policy for defining and enforcing MUFs on a given program should be developed early in the life cycle of that program or project. There's really no standard industry accepted way of defining and burning down MUFs during the design and test process. The Jitter Engineering Guidelines Handbook that I just spoke about, that should provide some guidance and recommendations for MUF applications. That's what we recommend. And the figure on the right-hand side here is an example of MUFs, how they change over time and how they change in magnitude as the system matures. One item that emerged late in the workshop, and we talked about a little bit afterwards, is what do we do for non-flagship missions? Really, at the workshop, we talked about the big, costly observatory class, Class A missions, we call them in NASA parlance, flagship class missions, where you have relatively large teams and fairly large resources, relatively large resources, I should say, to solve the jitter problem. And in this case, the comprehensive jitter solutions for flagship observatories, they're generally bespoke, one of a kind, physically large multi-instrument observatories such as James Webb Space Telescope. Those solutions are highly customized, they're mission unique designs, employ extensive modeling, analysis, and test, which, as we all know, is costly and time consuming. All this will drive the need for a paradigm shift to create lower cost jitter mitigation processes for what we've labeled as commercial class spacecraft. We felt as a group, the community should define the characteristics and features for a streamlined or tailored design for jitter process for these low cost missions. For example, industry could adopt an approach by simply baselining a minimum set of jitter mitigating features, such as a common isolation layer. So in summary, I'd like to close and outline a little bit of a go forward plan. So as I said, our Jitter Workshop was held in October of 2019. It revealed a community of subject matter experts eager and passionate to share their knowledge and to help prepare for the future. The workshop generated multiple findings and recommendations. You can find those all in the paper. The core team that planned the workshop has assessed the set of recommendations and we prioritize them for future action. Many of the recommendations will require a long-term strategy and some resources to implement, obviously. Two particular recommendations have emerged as fairly high priority and things that we can pursue immediately. And that is developing the Jitter Engineering Guidelines Handbook and to start planning for a second, possibly interagency, face-to-face spacecraft line-of-sight jitter workshop, perhaps hosted again by NASA or potentially by ESA in the near future, perhaps as later this year if the pandemic constraints are lifted. A supporting action will be to form a few small focused jitter working groups to create and execute a plan for following up with the recommendations listed above and to perform specific tasks. For example, we have spun up a small Jitter Engineering Guidelines Handbook working group that has started to outline and beginning to flesh out such a handbook. I think I'm running out of time, but I would like to briefly acknowledge the support of our peer reviewers. You see them listed here in the second bullet. Mike Agopian, a workshop participant, was responsible for distilling down and formulating these 5 best practices that I talked about earlier. Dee Bullock helped us prepare the paper and the presentation, and wanted to make this statement that the research described here was carried out in part at the Jet Propulsion Laboratory at California Institute of Technology under the contract with NASA listed here. So at this point, I think I'll wrap up, and I will stand by to take some of your questions in real time. Thank you very much for your attention. I hope you got something out of the talk, and let me know what you think. I always appreciate feedback from the audience. Thank you and goodbye.